I'm really excited to be here, really excited to be back at Stanford. So today I'm going to be talking about my research all about haptics. So I hope most of you know about haptics, but for those of you who don't, haptics is just everything to do with the sense of touch. So specifically, I work on the portion of haptics that deals with people. So we're going to be talking about basically how we can basically convince people that they're touching things that aren't there. So as Allison mentioned, I've historically have been a mechanical engineer, now in a computer science department. So my research kind of brings together parts from both of those fields, as well as from neuroscience and perception. So we both work on algorithms, we're building devices, and kind of putting all of these different components together to focus on creating realistic and immersive interactions. So we're really focusing on trying to create the most realistic interactions for the user. So today in this talk, I'm going to be focusing on talking about kind of how users perceive touch, how we can create haptic devices and hardware, and how we kind of work on signals and data to create more realistic actuation signals as well. So the first kind of application area that I want to talk about is in texture modeling. So texture modeling, what we're trying to do here is to create realistic feeling objects in virtual reality. So to make something feel like wood or like carpet or like metal, specifically like this specific type of metal or carpet or wood. And so what we're trying to do here is model specifically or recreate specifically what this object feels like as you touch it with a tool or rigid object. So the approach we take is called haptography or haptic photography. So what we do here is we take a snapshot of an interesting interaction, or actually record the data that's produced, or the physical signals, the touch signals, as well as the sound signals that are produced when you interact and touch the actual physical object. So the same way that you can use a camera to actually take a snapshot of an interesting visual interaction, here we can actually use a haptic camera or a haptic recording device to record that same information. And so I mentioned that we're recording or trying to model what people feel or what people perceive when they're interacting with objects through a tool. And so when you take a tool, you take a rigid object and I drag it across a surface, the tool tip, the tip of that rigid object, that hits all the little bumps along that surface. And that produces, these vibrations here. And so within the actual body of the pen itself, we have some accelerometers that are going to record those vibrations. And these vibrations encode the roughness of the surface. Now we have also a force torque sensor and a position sensor in the pen to record how the user is moving the pen, because we know that the feeling of the surface is not just a property of the pen and the surface itself, it's also a property of how the person moves the pen. So if we move fast or we move slow, or we press hard, we press softly, that changes the behavior of the vibrations that are produced. And so we need to make sure to capture these interaction conditions as well, these forces and the speeds at which the user is moving the tool, so we can make sure to include that information in the model. Because the ultimate goal of these models that we want to create with this data is to create a model that can then output fake vibrations or generate fake vibrations when a user is, say, touching an object in a virtual environment. So to fool the user into thinking they're touching the real object. Now, our senses are all intertwined. Okay, what we feel or what we perceive is not just limited to what we feel. Although I mentioned, we're talking about haptics, but what we see and what we hear also influences our perception of the physical interaction. So in addition to recording the actual physical vibrations, we have a microphone here to record the sounds of the introduction or of the interaction, to record the sounds that are produced when you drag the pen across the surface. And so our recording procedure is very, very simple. We need just only a small amount of data, about 10 seconds. So we take this recording device, we drag it across the surface in like a very smooth circular motion, and we get this, and we get some data out of it. So we get, with this recording device, we get both vibration data and we get audio data. And so this is the data that we recorded with, recorded from this piece of bumpy plastic, so rough ABS plastic. And so we can see that the audio data and the vibration data are related. And because the vibration data is actually pretty much just low frequency form of, or behaves like low frequency form of sound. And they actually are very, very correlated. So if I play the audio signal here, oops. So if I play that audio signal, that's the sound that's generated when you're dragging across the surface. So you can kind of get an idea of what that surface might feel like from just listening to it. And so I won't go into the details too much about, I won't go into too much details about how we create the haptic models, because that was the focus of my PhD work. But I want to go over now what is the, how we're actually modeling the sound portion of the work. So, because we have shown, so in my PhD work focused on modeling the vibration section of it, which was the focus of pretty much my whole thesis, which is a lot to go into now. But so my PhD thesis focused on modeling that vibration signal as a function of how the user moved with their force and speed. And we found that modeling that vibration signal as like an autoregressive process can create very, very realistic feeling virtual surfaces. But as if any of you have been running human subject studies, specifically those running in haptics, you know that you always have people wearing headphones playing white noise, because you never want to have the sound of, you never want sound to be an effect. So here, the work that my student Shihan Liu is working on is trying to actually add that sound information back into the interaction and trying to increase the realism of the virtual interaction by adding sound. And so to do that, we have to create a model of this recorded sound that can actually change based on the user's behavior. So that can change based on how the user is moving in a virtual environment. So we can't just record a bunch of data and store it. So we have to, because the user is going to be moving in different patterns, going to be and it's going to be moving for different periods of time. So we need to be able to create a model in such a way that we can generate an arbitrary sound data of arbitrary length. So we took inspiration from work in modeling sound textures, but when we talk about sound textures in the traditional like auditory literature, it is actually referring to textures or sounds such as footsteps or rain. So we took inspiration from those sound textures and used similar types of models to model the sounds produced from dragging a tool across our textured surfaces. And so, but our models are going to be much more complicated than the type used to model, say, footsteps or rain, because first of all, the data that we recorded is much more complicated because we can't have data recorded in a very controlled manner because people are very messy. So people are very messy in how they move. So we have data just recorded naturally. Just let the person move naturally and just move naturally basically in a circle and change their speed. So here we found that the sound does not actually change significantly with force, just with speed. So our input to our model here is only speed, and we get this output signal here. And so this is the output sound signal. And what we do is we send it through a segmentation algorithm that basically breaks up the sound signal into stationary segments, or segments where the sound basically does not change. And then within each segment here, we model each of these segments using a wavelet tree, where we're able to basically break it down into its components. So we're able to store it and store each of these wavelet trees as saying that this is a wavelet tree for how the texture should sound based on the speed at which the user was moving during that original recording. And so now we have all this very complex, this very high dimensional data that's stored as a lot smaller number of data points. And then when we're rendering it, what we do is we take velocity, we do velocity detection, so figure out what is the speed that the person is moving in the virtual environment, select the appropriate wavelet tree, add some stochasticity to it, because we want to make sure to add some randomness into whatever noise we're generating, because people are very, very susceptible to knowing when things repeat, or to knowing when sound clips repeat, when vibration repeats. So we make sure to add some stochasticity when we regenerate with the wavelet tree. Make sure we do some blending here between adjacent wavelet trees that we have to blend together so that we don't have like jumps within the sound signal that we are generating. And then we send it to the sound stream. So we generate about 100 data points at a time. So we are able to update. So we're able to update this user's velocity, pick a new appropriate wavelet tree, and generate just pieces of sound at a time. And so I'll show you a quick video here of how this works and compare it to the original recorded sound as well as direct playback. This is the original sound. And so our method is, so it's a little quiet, but with our method, we're able to actually very accurately match the user speed. And so which you're not able to get. If you kind of could hear the direct playback, which is just direct playback of sound and not adding that stochasticity to it, not doing the initial steps of the mid steps of the wavelet tree modeling, created this very artificial sounding sound or texture. So with the actual results, the actual study that we ran here, we were able to find that our results, our methods were very realistic and actually significantly improved the realism of the virtual interactions with the virtual textures and the virtual sounds over not playing any sounds. So we're now continuing to look into this sound modeling to figure out how important is the sound to the interaction, and looking at modeling not just dragging sounds, but also tapping sounds as well. So now moving on to more talking about texture modeling. So previously I was talking about recording data. So recording data, needing to actually record and have the surfaces in front of you and have this big elaborate setup for recording data. So that's expensive. So it's very expensive to have all those sensors, like the force sensors and everything. So can we have a way to create new models of textures without having, without needing to have the recording setup? So the old way of doing this modeling would be to have some kind of physical model, mass spring dampers, where someone would sit there and manually tune all these knobs to figure out until something felt good enough. But the problem is that people are really bad at tuning. People are really, really bad at tuning because they don't know what's wrong. People are really good at saying when something is wrong, but not really good at articulating what is wrong. So instead, again, this is for my student Shihan, who came up with this method of preference-driven tuning for the texture models, where it allows users to answer just yes or no questions. It's basically allowing us to iteratively tune textures by just choosing the best one from a set. Because people are very good at choosing the best one rather than telling you what's wrong. So what we did is first we started out with this huge data set of textures that I created in my PhD. So it's a set of 100 sets of texture and texture models, friction models, and sets of texture data. And so the haptic texture models are autoregressive models. Then we have the friction coefficients. And the autoregressive models are stored as the autoregressive coefficients. Friction models are stored as the Coulomb friction coefficients. And so what we do is we use this set of 100 texture models, and we use it to train a deep convolutional generative adversarial network, or DCGAN. So basically what we're trying to do here is we're trying to train it what a texture model is and how a texture model behaves. So because we have a lot of information. So a texture model or model of one texture is not just one thing. So when we have this set of say autoregressive models for the textures, it's actually a set of say 30 autoregressive models where each autoregressive model describes how the surface behaves at one particular force and speed. And then there is some behavior that says, okay, this is how the frequency information of the model should change with increasing force or increasing speed. And so for us, trying to figure out all of that information by ourselves is really challenging. Trying to figure out all of those natural behaviors, or all those behaviors, really challenging. So instead, we send it through the DC GAN and allow the DC GAN to kind of learn everything for us. Learn, first of all, how the texture models should behave, as well as what that kind of relationship between force and speed is. So we have the generator is going to map the latent space to the texture models, given the texture models we feed it in. And the discriminator is judging whether a texture model is real or not based on the data we feed it in, as well as additional rules that we give it, such as the fact that all autoregressive models must be stable. So after we use all of our data and models to train the network, then we can use this to generate new models. So we can use this to generate a new texture model for a texture that we have never seen before. And so what it does is it first generates 3 arbitrary textures. So so it works on an evolutionary search method where it generates first 3 output textures that it then it presents to the user. It says, user, here are 3 textures. Then the user feels the real texture and 3 textures using a force feedback haptic device that has a vibration actuator on it. Then the user will says, this is the one that feels the closest. Out of this set of 3, I like texture number 2. Then they'll select that one. This information is fed back to our network. It goes through it updates again. Then it generates 3 new textures. The user feels these 3 textures again, then selects their favorite one. Then it goes through this process again and again. So when we ran our user study, we found that users actually only need about 5 iterations. It only need about 5 iterations until it is able to, until they find something that they feel is realistic enough, that closely enough matches the real texture. And so in addition, the DC GAN handles the texture, the vibration model portion of it. And then we also have manual friction tuning, where they have, say, a slider here where they can manually change the friction of all 3 models. And so this here is what is kind of what their UI looks like, where they have the 3 texture patches, and then they have a friction controller. And so they feel the texture patches, they change the friction, then they select which one feels most realistic. Then the system updates the 3 texture patches automatically. Then they feel all 3 again. So they're feeling them with the 3D Systems Touch device, which is a force feedback device, which we attached a vibration actuator to the tip of the device. And then they feel the real texture with a modified handle of the force feedback device, which we added a tooltip to. So in the study that we ran, they modeled these 5 textures, which are different, not included in the database. And then we ran so we had 5 subjects come in, and so we ran the first study where we had 5 subjects come in, do the actual training of the models. So we created now 5 separate preference-driven models for each of these 5 textures. Then we ran a second study where we had another set of participants, another set of 20 participants, come in and test the realism of those 5 textures compared to a data-driven texture which we created. And our goal here was to figure out how well does our preference-driven modeling do. So ideally, our preference-driven modeling would be better than or no worse than the data-driven modeling. So here we've broken it up into comparing, so the yellow is the comparison of the data-driven model to the real texture, and the purples are all comparing the preference-driven model to the real texture. So these are all compared to the, so these are all here compared across the 5 textures. So we have 5 different preference-driven models. And so we can see that for the majority of the preference-driven models, and again, these are preference-driven models created from people who had no training. So had no training in no experience in haptics, no training in creating the models. And so for the circles are the ones where there is no significance. So the preference-driven models significant, like there's no significance between their performance in realism and the data-driven model. The one with the stars are where this preference-driven model did significantly better than the data-driven model. So we can see that for the majority of the textures we tested, we're about comparable. We're at about comparable behavior between our preference-driven model and the data-driven model. Where we have the biggest difference here is this first column with the ABS, where the majority of the models were significantly worse than the data-driven. But where this now comes out, or where we dug deeper into this, is we looked at now the perceptual dimensions of these different textures, where in addition to realism, we had participants rate the roughness, hardness, and slipperiness of the textures, and found that for the ABS, the biggest difference here is in the actual, was actually in the roughness and the hardness. So here, or actually here, no, it wasn't, sorry, this is the orange is the real surface. So there was no difference between the data-driven model and the perceptual-driven models, and data-driven model and perceptual-driven models for ABS, for roughness or hardness. So we found that within the actual perceptual dimensions of the textures, there was no difference. So in the actual dimensions that we care about, there was no difference. So we were actually capturing, so participants who were creating the models for the preference-driven were capturing, say, with roughness, they were capturing the frequency information of the ABS correctly. The issue we were running into, or when we dive more deeply into the models, where the split happens and why we see that big difference between the realism of the data-driven and the preference-driven model is the amplitude of the vibrations. Where the preference-driven, people who did the preference-driven models tend to over-exaggerate the vibrations, tend to make the vibrations too strong. And that's what causes that mismatch between the realism. So that is something that we are going to look at in the future, is looking at providing additional training, as well as looking at providing specifically an amplitude, not just a frequency tuning, but also an amplitude tuning to see if we could better match some of these rougher surfaces like the ABS, which match along the frequency, but do not match along the amplitude. Yes?
how you set up the experiments and then generating the data and creating these types of models, is how the human users' preferences or interactions change over time. So I mean, you had said that like 5 preference choices were enough for them to for the thing to stabilize, I guess.
Yes.
But at least from my own perspective, I have no clue what this chair feels like, but if I touch it for a while, I'll kind of have a model of this chair. But like, I won't remember that tomorrow, right? So I'd have to relearn that model. So is one takeaway from this, like, maybe you can just tell people what things feel like virtually? Or like, how would you consider the longer term temporal aspect?
Very, very good question. So there is actually a lot of research into haptic memory. And so haptic memory only lasts maybe 30 seconds. And so it's not very long. And so they're constantly having to switch back and forth. And so it's not, so yeah, so they have both in front of them at all times. So they have the real texture and the virtual texture in front of them at all times. So they feel the real texture, they feel the virtual texture. They feel the real texture, they feel the virtual texture. So asking them to remember how something feels, yeah, would absolutely not work.
Okay, cool.
Yeah, okay. So now moving away from texture, I want to talk about modeling some other aspects of surfaces, which is hardness and stiffness. And so hardness and stiffness are actually 2 different things. And so we think of them as being one thing in terms of haptics, kind of the terms hardness and stiffness as being interchangeable. But stiffness is actually how much an object resists elastic deformation. So basically how squishy something is, and that's felt as a force. Whereas hardness is how much an object resists localized surface deformation, which is felt as tactile cues. So that's felt as like can be felt as like the impulse of vibration that you get when you tap on a surface. That's like the hardness, whereas how squishy something is, that's like the stiffness. So my student Nagma Zamani has been working on how do you combine both the surface, render both the hardness and stiffness together. So we all know, those of you who have been working with force feedback devices know that force feedback devices are very limited. Like they're limited in terms of their motors, and so they cannot output high forces because of stability issues, because of quantization errors. So what she's been trying to do is create a system that can render, say, stiffness with the motors of the device itself and hardness with some external surface attached to the device. And so what we're actually creating here is what's called an encountered type haptic device. As the reason it's called an encounter type haptic device is because unlike normal force feedback devices where you grab the handle and you're always holding onto the handle, this one you're in free space. So you're in free space until you come along until you reach, say, a virtual surface that you want to touch, and then you encounter the haptic device when you reach a virtual object in the virtual environment. So the way this surface works, so this is a no-vent Falcon that we turned 90 degrees on its side because this x-axis is the one that has the highest force output. So we turned it on its side, and we're working basically with tapping interaction right now. And so we have an external pen that is ungrounded, it's untethered, it's not attached to the device at all. And what we have here is we attach different materials to the surface with different hardnesses. And so hardness, if any of you are mechanical engineers, hardness is measured by the Shore scale. And so we attach different materials here on the end effector that are measured on different Shor scale, from like Shor 0 to like the Shor A scale. So we can get a very wide range of hardnesses. So it's kind of, the interaction we're creating here is kind of a combination of encounter type haptic devices as well as haptic augmented reality, because we are using the actual motors of the using the motors of the device themselves to display the stiffness, say the squishiness of the material, and we are creating, and we're actually physically changing the end effector here to change the hardness of the material. And so we ran a study. This was just presented at a Haptic Symposium this year. And so we ran a study where we compared our rendering method with this new encounter type haptic device with traditional haptic rendering methods, which are like the traditional Hooke's Law spring rendering, as well as Hooke's Law like spring damper rendering, as well as with the spring rendering plus tapping transients, which is what's typically done, what's been traditionally done to provide some hardness information, which is, you have the Hooke's Law, which provides, say, a force proportional to your penetration into a virtual object. And then tapping transients or event-based transients are these transient forces here that are produced and played right only when you first come in contact with an object, that are supposed to increase the perceived hardness of an object. And so these are the traditional haptic rendering methods that are kind of the state of the art, say, in terms of displaying virtual objects, or the most common methods of displaying virtual objects. So we wanted to compare our method of combined hardness and stiffness rendering with these traditional methods to discover, how well does our system do compared to these traditional methods in matching both very soft surfaces and very hard surfaces. And so these are the 6 surfaces that we included in our study. And so it's a combination of both hard, soft, and as well as hard and soft surfaces, as well as changing the underlying stiffness. And so the top row, they are backed on foam. And so there's actually foam underneath the materials, which changes the stiffness, which changes the underlying stiffness between the material, but does not change the hardness of the material on top. And then the bottom row is a very high stiffness material underneath. So we have wood underneath them. So for example, wood on wood is a very high stiffness material and a very hard material, whereas insole on wood is a very low hardness material, but a very high stiffness material. And so we wanted to see, based on all of these possible combinations here, how does our system kind of behave in terms of changing both the hardness and the stiffness. And so with our device, we tuned the stiffness through a staircase method to find the appropriate stiffness to display for our like Hooke's Law rendering. And then for the hardness for our system here, we chose appropriate Hooke's Law, where we chose appropriate Shor hardness actual surfaces that we directly attached to the end effector. So each of these 3 materials here, insole, felt, and wood, have different materials that were manually attached to the end effector when we were rendering them. So in our study, the subjects would tap on the real materials and then would tap with the virtual system and then would compare the realism in terms of realism between the real material as well as tapping with the virtually rendered material to figure out which one, to rate how realistic it felt. And so for all of the materials, our system, which is the encounter type haptic devices, were rated most highly realistic, even when we changed the underlying stiffness. So even if we did like a low stiffness or high stiffness, these were rated, our encounter type haptic device was significantly rated as more realistic than the traditional rendering methods, even more realistic than the tapping transients method, which is considered which has been considered kind of the state of the art and increasing the perceived hardness of objects. And so here, the second slide here shows shows the rating comparing the hardness of the original surface and our material and the rendered surface. So ideally, you want these along 0. You want these at 0, so there would be zero change in hardness. And so here we also had the closest match in hardness, except for felt on foam, which here we were just a little bit too hard, which probably was due to just choosing the material that we put on top incorrectly. And so I planned too much to talk about today. Okay, I'm going to talk about one last project, and then I'll open up for questions. So one last project I want to talk about is data-driven social touch, which I actually started in Ellison's lab here. And so what we're trying to do here with the data-driven social touch is to study how people communicate to one another through touch and figure out how we can recreate that information virtually. And so this was a study that I did in here at Stanford in Allison's lab, where we recorded, we had this very nice sensor sleeve that we recorded the information and were able to then map it down to very sparse array that we conveyed with an array of 8 voice coil actuators. And we're focusing on conveying specific emotions that we asked participants to record with that sensor sleeve. And so this is the results from that paper, where we found that we were able to get approaching human accuracy in displaying emotions with that virtual device. Now, I have been continuing on that research with my student Xin Zhu, and what we're focusing on now is trying to actually do more of a one-to-one mapping of data recorded to output, so that we can focus on real-time transmission of touch. So rather than trying to have this very big, bulky recording sensor, focus on something that's much smaller and compact, so that we can do a real-time transmission of touch, so that someone touches a set of haptic sensors, and then it can be, with very minimal delay, then immediately output on a set of voice coil actuators. And so the sensors we're using is this array of 8 force sensing resistors that we created in this armband. And so to record the system, or to record the touch, you can now touch the armband directly. So you touch the armband directly, you can squeeze it, poke, stroke, pat, and then it records that force. It can record that force profile information, and then it's processed and then gets sent to the actuator sleeve. So we're using the same actuator, or same setup of the actuator sleeve, which is eight voice coil actuators, which they are capable of outputting vibration, but we're actually driving them at very low frequencies. So they're able to we actually move them up and down at very low frequencies to press into the user's arm. And so this is what the data looks like. And so this was just published in Frontiers in Computer Science. And so this is what the data looks like for the different 5 different social touch gestures that we looked at, which is stroking, massaging, poking, squeezing, and patting for the 8 voice coils. So we basically looked here at a 1-to-1 mapping of FSR to voice coil, and then as well did some processing to get some smoothing in between to make sure that things, for example, like the stroking motion, to make sure we got smooth motion between them. And then in the study that we ran, we wanted to specifically look at how does speed affect the perceived emotion. So we recorded the data ourselves, and we're looking at how does speed change how people perceive the emotion of the touch. Because we know that speed has some effect on the social touch because of the importance of the CT afferents, or C tactile afferents, in social touch. So the C tactile afferents is one of the mechanoreceptors that's specific to social touch, and it's most sensitive around 1 to 10 centimeters per second, or that's when it's like preferential, that's like its preferential speeds. So we know that speed is going to have some effect, or that was our hypothesis. So we wanted to study what was kind of that effect of speed. So we took original recordings of those 5 social touch gestures, and then we sped them up and we slowed them down to figure out, and then we had people rate the affect and valence. And so this is the scale we used to rate affect and valence. We found that, I know in the previously we had them rate separately, but we found this one was actually a lot more, was actually a lot easier for people to use to rate affect and valence together, so that they could choose like what emotion did they think that the touch was trying to convey. And so we found actually very strong results with the speed. So especially for the emotion, for the gestures that are more emotionally attuned, such as massaging and stroking and patting, there was a very, very strong effect with speed. So F is when was faster and S was slower. So stroking here, we saw, valence here, negative valence is negative emotions, positive valence is positive emotion. So we see that with stroking is fast, it's a negative emotion, stroking is slow, it's a positive emotion. And we see similar trends here with massaging and patting. But for gesture like poking, which is more attentional gesture, like not really an emotional gesture, we saw no effective speed. And so we saw similar effects with arousal, where you get high arousal at high speed and low arousal at low speed. So we saw very, very clear trends of speed here, which we were hoping to see. And it's always good when you run studies and you do see those speeds, or you do see those trends. So I'm out of time. I want to leave time for questions. So I won't. I won't go through the last one, but we also have another project where we use vibration to reduce simulator sickness in VR. So unfortunately, I won't get to this project, but I want to thank all of my students, everyone that, of course, I could not have done all this work by myself. So I want to thank all my students and everyone at USC, and I'm happy to take any questions.
Questions, please.
Yeah, I have a question about the last part of your presentation. I'm curious why you chose the 5 gestures among the other gestures.
Oh, why we chose specifically those?
Yeah.
Because those 5 gestures, those are common ones that are done on the forearm as ones that are shown to be traditionally used in social touch.
Great. Other questions? Yeah.
Hi, thank you for your talk. I was wondering for the first part of your presentation, for the person dragging the probe along like the material, I was wondering why, I noticed that like as they moved, sometimes they would speed up, they would slow down. Do you find that that variability in the motion like affects the profile that you're analyzing, or like why not like have like say a mechanical arm like perform that motion?
Very good.
There's consistency with that.
Very good question. Okay, so we have what we consider like the force speed space, which is kind of the area of motions or input conditions that we expect the user to use when interacting in VR. And so if the user is going to use that motion in VR and virtual reality, then we need to make sure that we collect data. Then we need to make sure that we have collected data and have modeled that interaction. So that's why there's speed up and slow down and pressing harder and pressing softer. So I recorded that data, and I made sure that I got very, very good at making sure at changing my motion in such a way that within 10 seconds I was able to pretty much span the entire force speed space that we expected people to use during interactions. But the reason why we don't have, say, a mechanical arm recorded, one of the reasons is, first of all, it won't quite feel right because you won't get the same like impedance, and so you wouldn't get the correct vibration profile. Another is that there's going to be vibration in the arm, and so then you would end up recording the vibration of the arm. So I know actually in the work that I did in my PhD, the student who was doing the project before me, the first time he took the data, they had a rotating drum. So they put the textures on a rotating drum and then had like a fixture just holding the pen at a constant force with a rotating drum under it. And then you play it back and you can hear the drum rotating, or you can actually see the drum rotating in the data. And so we tried a couple different ways of recording the data, not having user in the loop, which would be better because users are people are very, very messy. But just found that we couldn't get good data that way.
Thank you. Another question? Yeah.
Yeah, thanks for the talk. I was wondering if you could talk a bit more about, on the first part, how maybe using just auditory cues or auditory and haptics or just haptics would compare in their success rate for like being able to replicate the virtual material and like have the user correctly identify it.
Interesting. Okay, interesting question. Yeah. So that's what we're looking into now. We're actually getting ready to run a study to look at the relative importance of haptics versus audio. And our theory is that it's going to be dependent on like how much audio or how strong of an auditory signal that it produces. So we think that for rougher materials, sound is going to be more important than for smoother materials, just because it produces more because it produces a stronger sound. But that's something that we're going to be looking into very soon.
Thanks. Any others?
Any questions on Zoom?
Oh yeah, are there any questions on Zoom? I think you can just unmute yourself and ask if there's a question on Zoom. And if not, then, Oh, yeah, go ahead.
Uh-huh.
Why were there 8 actuators? Do you think that there's more that would be helpful, or was it a limitation from form factor?
Yeah, it was a limitation on form factor for the 8 actuators. That's the amount you can physically fit on an arm. Of course, if you're a taller person, you have a bigger arm, but when I was making that slate first in Allison's lab, we tested on many people in the lab, and even on that's the number that would physically fit. We tried using smaller actuators. There's actually a smaller version of those voice coils available from the company. The problem is that with the smaller voice coils, you have a smaller coil, and which means they're not as strong. And so those could be used on the hand, but are not strong enough to be perceived on the arm. And so that's kind of why we chose that. That's why we chose those voice coils, and then the spacing is chosen because that's as close as you can physically put them together.
Okay, let's all thank Heather.